Every time you make a decision, whether it's simply choosing to turn left or right, it's possible that somewhere in the universe, another version of you is choosing the opposite path. Does this sound like science fiction? For many of the world's leading physicists, this isn't fantasy, but a real possibility. We may be living in one of countless parallel universes, each with a different version of history, of reality, and even of yourself. Today, we will explore one of the most audacious ideas in modern science, the multiverse theory, where the boundary between science and philosophy blurs, and the question, what is reality, may have a completely unexpected answer. The foundation of reality, when quantum mechanics unlocks infinite possibilities. To understand why scientists are seriously considering the existence of a multiverse, we must return to the strangest discoveries in the history of physics, quantum mechanics. In the early 20th century, as scientists began to explore the microscopic world of atoms and subatomic particles, they discovered that the familiar laws of physics suddenly no longer applied. At the quantum level, a particle can be in multiple places at the same time, a phenomenon known as quantum superposition. An electron isn't at a specific point until you observe it. Before that, it exists as a probability cloud spread out in space. This sounds absurd, and even Albert Einstein was uncomfortable with it. He famously said, "God does not play dice," alluding to the strange randomness in quantum mechanics. But experiment after experiment has consistently confirmed the quantum world truly works this way. The real problem lies in the question, what happens when we observe a particle? In traditional quantum mechanics, known as the Copenhagen interpretation, it is believed that upon observation, the particle's wave function, which describes all its possibilities, suddenly collapses into a single state. But why? How? No one really knows. This is called the measurement problem, and it has been debated by physicists for nearly a century. In 1957, a young graduate student named Hugh Everett III proposed a bold and controversial solution. Perhaps the wave function never collapses. Instead, every time a measurement is made, the universe splits into multiple branches. In one branch, you observe the particle at position A. In another branch, you observe it at position B. Both outcomes happen, just in different parallel universes. This is the foundation of the many worlds interpretation. According to this view, every moment, the universe is branching into countless versions. Every quantum possibility, no matter how small, is realized somewhere. One version of you is reading this article, another version closed the browser a minute ago, and yet another may have never been born because some random event in the past played out differently. Does it sound crazy? But the many worlds interpretation is not science fiction. It is a completely valid mathematical interpretation of quantum mechanics, and more theoretical physicists are seriously considering it. A 2013 survey at the Quantum Physics and the Nature of Reality conference found that about 18% of physicists believe in the many worlds interpretation, a non-trivial percentage in a typically cautious community. But quantum mechanics is just one of many paths leading to the idea of a multiverse. Another path comes from the theory of the origin of our own universe. Recall that our universe went through a phase called cosmic inflation right after the Big Bang, when space expanded at an unbelievable rate. But what if this inflation process didn't stop everywhere at the same time? According to the theory of eternal inflation, developed by physicists Alan Guth and Andre Linde, inflation is still ongoing in most regions of space. Only in some random pockets does inflation stop, forming universes like ours. Imagine inflation as a boiling ocean. Most of the ocean is still boiling vigorously, but occasionally bubbles appear where the water cools down and stabilizes. Each bubble is a separate universe, with physical laws, cosmic constants, and structures that could be completely different. Our universe is just one of countless such bubbles, floating in an ocean of eternal inflation. What's remarkable is that these bubbles may still be forming right now, and will continue to do so forever. Some bubbles may have physical laws that allow life to exist. Most others do not. We exist in a lucky bubble, simply because if we didn't, we wouldn't be here to wonder about it. This is called the anthropic principle. We observe a universe suitable for life because only such universes have observers. But there's another, even stranger type of multiverse, the mathematical multiverse. Physicist Max Tegmark proposes that every self-consistent mathematical structure corresponds to a real universe. If you can write down the equations describing a reality, no matter how different from ours, then that reality exists somewhere. In this view, reality isn't just described by mathematics, reality is mathematics. So how many types of multiverses are there? Tegmark has classified them into 4 levels. Level I, distant regions in our own space, beyond our observable horizon, where initial conditions are different but the laws of physics are the same. Level 2, bubble universes from eternal inflation, with different physical constants and possibly different laws. Level 3, the branches of the many worlds interpretation, where every quantum outcome is realized. Level 4, all possible mathematical structures, including universes with completely alien laws of physics. From quantum mechanics to cosmology, from mathematics to philosophy, the idea of a multiverse emerges from many different directions. But is there any real evidence? Or is this just beautiful but untestable mathematical speculation? Hidden clues. Searching for traces of other universes. One of the biggest challenges with the multiverse theory is, how can we test something that lies outside our observable universe? If parallel universes cannot interact with us, are they any different from imaginary stories? However, scientists don't give up easily. They have been searching for subtle traces, scars that other universes might have left on our own. And surprisingly, some clues have been found. First are the cold spots and anomalies in the cosmic microwave background, CMB. Scientists have created detailed maps of the CMB, the ancient light from 380,000 years after the Big Bang. Most regions in this map have a uniform temperature, with only minor fluctuations. But there are some unusually large regions that are colder than expected, known as the CMB cold spot. Some physicists, including Laura Mersini-Houghton from the University of North Carolina, propose that these anomalies could be traces of a collision between our universe and another bubble universe in the early stages. When 2 bubbles collide, they leave a bruise on the fabric of space-time, and this bruise could manifest as anomalies in the CMB. Of course, this is still highly speculative. There are other explanations for the cold spot, and there is no consensus in the scientific community. Another clue comes from measuring the fundamental physical constants. Our universe appears to be incredibly fine-tuned to allow for the existence of life. For example, if the strong nuclear force were just a few % stronger or weaker, carbon atoms, the foundation of life, could not form. If the cosmological constant, dark energy, were slightly larger, the universe would have expanded too quickly for galaxies to form. Why do these constants have such just right values? One explanation is through the multiverse. If there are countless universes with different constants, then the fact that we find ourselves in a universe suitable for life is no longer a miraculous coincidence. It's simply the anthropic principle. Universes unsuitable for life still exist, but there's no one in them to wonder about it. However, this is a controversial argument. Many scientists argue that using the multiverse to explain fine-tuning is giving up on the mystery instead of searching for a deeper physical explanation. But proponents counter that if the multiverse is real, then it is the deeper physical explanation. In quantum mechanics, some experiments have also been proposed to test the many worlds interpretation. One idea is to create a quantum system large enough to directly observe superposition, a state where an object is in multiple places at once. If we could prove that both branches of a quantum measurement continue to exist, instead of one collapsing, it would be strong evidence for many worlds. Recently, physicists have created superposition with increasingly large objects, from single photons to complex molecules and even microscopic objects. In 2019, a research team in Vienna created superposition with a molecule containing nearly 2,000 atoms. Each such step brings us closer to testing the limits between the quantum and classical worlds, and possibly finding clues about the existence of parallel branches. Another line of research involves string theory and high-energy physics. String theory predicts that there may exist a vast landscape of about 10 to the 500 different solutions, each corresponding to a possible universe with different laws of physics. This is known as the string theory landscape. If string theory is correct and this landscape exists, then the multiverse is not just a possibility, it is an inevitable consequence. Experiments of particle accelerators like the Large Hadron Collider, LHC, are searching for signs of extra dimensions or new particles that could hint at larger structures beyond our observable universe. So far, there have been no definitive discoveries, but each experiment narrows down the possibilities and helps us better understand the fundamental structure of reality. Of course, all these clues are still very vague and have other possible explanations, but the fact that we can even discuss how to test the multiverse, something once considered untestable, is a significant step forward. Science is slowly turning a philosophical idea into a researchable question. Debate and the future, when the line between science and philosophy blurs. The multiverse theory is not only scientifically controversial, but also sparks deep debates about the nature of science and reality. One of the biggest criticisms is, if we cannot directly observe other universes, is the multiverse still science? Or is it just a beautiful but untestable mathematical story? The renowned physicist Paul Steinhardt once called the multiverse theory unscientific because it seems to explain everything and therefore explains nothing. If every possible outcome happens somewhere in the multiverse, how can we make falsifiable predictions, the gold standard of science? Proponents counter that science is not just about what we can directly observe, but about the theories that best explain the data we have. If eternal inflation or quantum mechanics, both of which have been extensively tested, naturally lead to a multiverse, then we should take that consequence seriously. Moreover, as we've seen, there are potential ways to search for indirect evidence through anomalies in the CMB or quantum experiments. Another debate revolves around the philosophical implications. If there are countless versions of you in different universes, what does that mean for the concept of personal identity? If every possible choice is made somewhere, do our decisions still have meaning? Some philosophers argue that the multiverse devalues individual action, while others counter that what matters is what you do in this universe, in this branch of reality. There is a deeper question. If countless versions of you exist, which one is the real one? Or are they all equally real? According to the many worlds interpretation, all branches are equally real. No branch is more special than another. From the perspective of each version of you, they are the real person, and the others are unrealized possibilities. But from a more global perspective, they are all part of a single universal wave function. This also raises questions about probability. If every outcome happens, why do we observe some outcomes to be more common than others? The many worlds interpretation explains this with the concept of the thickness of the branches. Branches with a higher amplitude, according to the wave function, correspond to the higher probabilities we experience. But this is still an active area of research, and not all physicists agree on how to interpret probability in many worlds. Looking to the future, there are several promising research directions. The next generation of CMB observing telescopes, like the Simons Observatory and CMB-S4, will have much higher sensitivity, potentially detecting more subtle signs of cosmic collisions. Quantum experiments are progressing towards creating superposition with larger and larger objects, which might one day reach a scale where the differences between interpretations can be tested. In string theory, researchers are trying to better understand the string theory landscape and whether there's a way to narrow down the number of possible solutions. If they can find principles that constrain what kind of universe can exist, it would help turn the multiverse from a vague idea into a more concrete, predictive theory. Some physicists have even proposed creative ways to communicate with other branches in the many worlds, although this remains highly speculative. The idea involves using quantum computers, devices that harness quantum superposition to perform calculations. Some suggest that a quantum computer borrows computational power from its copies in parallel branches. If true, this would be strong indirect evidence for many worlds. However, most physicists believe that quantum computers can be explained without resorting to the multiverse. Ultimately, the multiverse theory forces us to confront an ancient philosophical question: what is reality? Throughout history, humans have believed that what we see is all that exists, but science has continually expanded the boundaries of reality. We once thought the Earth was the center of the universe. Then we learned that the Sun is just one of billions of stars. Then we discovered that the Milky Way is one of trillions of galaxies. Each time, reality became bigger, vaster, and stranger than we had ever imagined. The multiverse could be the next step in that journey. It is an idea that is both humble and arrogant. Humble because it suggests that our universe, with everything we know, is just one of countless many. Arrogant because it asserts that humans can reason about what lies beyond the limits of observation. Are we living in one of countless parallel realities? For now, we don't know for sure. We may never know definitively. But the very act of asking the question and searching for the answer with mathematics, experiments, and observation is what science is all about. If the multiverse is real, the consequences are profound. It means that every possibility exists, every road not taken, every version of history, all are playing out simultaneously. The universe is not just bigger than we think, it is infinitely bigger than we can possibly observe. But even if the multiverse does not exist, the value of exploring the idea is immeasurable. It forces us to think deeply about the nature of reality, the meaning of existence, and the limits of human knowledge. It reminds us that the universe may be far stranger than we can imagine, and that is what makes science so compelling. Perhaps, somewhere in a parallel universe, another version of you is reading a different article, or not reading at all. Perhaps elsewhere, history has unfolded differently. Dinosaurs never went extinct, or humans discovered faster-than-light travel. And perhaps, in a distant universe with completely different laws of physics, forms of life and consciousness we cannot possibly conceive of are wondering if other universes like ours exist. The multiverse theory is a reminder that the story of reality is not yet finished. Every answer we find opens up 1,000 new questions. And that is the beauty of science. Not in what we already know, but in the mysteries that are still waiting to be discovered. Of all the infinite realities that may exist, the most wonderful thing is that in this one, right now, we have the ability to wonder about it all.